Hello, good morning, good afternoon, good evening, wherever you find yourself. You are welcome to the 11th webinar series of the University College of Water Science and Engineering. My name is Moses Kabir. I'm the technical support for UWSE. Today we have in our midst Mr. Ahmad Babamala. He's a PhD candidate in global navigation systems at the Beihang University in China. So he'll be taking us through the evolution of GNSS and GPS technology and its application from ancient times to the present.
My name is Baba Ahmad Mala. I would first of all like to extend my profound gratitude to the University College of Science in Ghana for giving me and providing me the platform to present my topic of discussion, evolution of GNSS, GPS technology and its application from ancient times to the present. I am from the Regional Center for Space Science and Technology Education in Asia and the Pacific. So I would like to say something about GPS and GNSS in general. So the good thing about GPS is it has a profound GDP of almost 4% globally. But in Africa, we have a deficit of only 3% reference station are just in Africa. So what does that tell us? It's not just about the technical discussion, it's about the sovereignty of data. If we own our data, we will now predict our agricultural product, our productivity, and so on and so forth. So, as I said earlier, I am from the Regional Center for Space Science and Technology in the Asia Pacific in Beihang University. My journey started from software engineering to communication engineering. That is from Sharda University in India to Wuhan, and then now I'm a PhD candidate at Beihang University. So the objective of our webinar, we are going to discuss the historical mastery of the GNSS journey to enhance critical thinking and then to promote communication skills and build network. So our learning outline has introduction, ancient navigation foundation, pre-GNSS electronic era, the birth of GNSS and its development, and then the application. So here you can see that in the outline, I have made it in such a way that, okay, in each and every outline here, there is subtopic. You can see now we are going to be discussing about definition of GNSS, definition of navigation, then next positioning, and then timing, which are profound for the GNSS. So let's say now here we are looking at a screen where there is showing a tree, a line. It's like a navigation line. So here is to tell you, okay, if we want to move from point A to point B, what is the easiest route to take us from point A to point B? Here you can see, okay, the car is moving from point A to point B. And then next, we are having another route is taking us from point A still to the same point B. But you can see the second one is more, it's more easier from the point. That is how navigation works. So the definition of navigation is a process of planning, reading, and controlling the movement of a craft, like vehicle, person, or object from one place to another, according to Bowie in his book in 1995. In GNSS, that is Global Navigation Satellite System, literature navigation also refers to determining the course or heading of movement. The etymology here is navigate. The word navigate comes from Latin, means a ship. And then we have agri, which means to move or to drive. And then thus, we have the art of science of directing a craft as it moves its path, according to Ritchie in 2007. So next, we are going to talk about positioning, which is another key point of navigation. Here, we can see in our positioning is to like say, okay, where am I? Where is here? Okay, you are here, then where is here? So it is a process. It is a process that determines the location of a point relative to the known positions. Real-time position refers to the obtaining location data instantly with no delay between the object's actual positioning and its recorded coordinates. So in GNSS, getting into position rather than just locating a point. It may include not just coordinates, not just the latitude, longitude, altitude, but also bearing, direction, and movement. And as I said, positioning is relative to GNSS. That is to say, okay, in positioning, you are not just going to say, okay, you are here, but rather you are going to say, okay, the positioning is going to tell us that you are 3.2 meter northeast yesterday's location, and so on and so forth. Next, we are going to talk about timing. So the timing here, we have the astronomical and then the atomic. The astronomical is based on Earth rotation. That is the celestial clock, and then the atomic time, which is ultra precise clocks like the GPS satellites. It's an ability to acquire and maintain an accurate and precise time from a standard clock. The reference, the coordinates, the frequency. Next in our line is ancient navigation foundation. So this is like the foundation of navigation, how the our ancestors are navigating from point A to point B. So from the ancient navigation, we have history of navigation, the tools they are using, and then the challenges they faced. So here in the picture, we are going to see a mountain and a lot of, like it's like houses. So what to say here is that it's a landmark navigation. There is a landmark. So if you want to travel from point A to point B, you know that, okay, you are going to follow this route. There is a mountain, so you can follow back through knowing the mountain and so on and so forth. The first record of boats large enough to carry goods for trade is around 3,500 BC. And this will mark the birth of navigation. That is the real history of navigation. So next, imagine you are a navigator on the open ocean thousands of years ago, no GPS, no maps, just sky above you. How will you move, or how will you sail from the sea? So what they do here is that they keep on looking at the sun, the stars, to help them navigate from their respected destination to another destination. So here is another picture of sailors, which is showing they are crossing the ocean, yet no, they are playing in a safe, hugging the coastline and so on. So what they do here is the early sailors, they stay close to the shore. They never sail at night because they took in further way, entire fleets will stay in port during the winter months. During the winter, they have a lot of issues. They can't navigate as they're supposed to. So next, we are going to talk about another celestial navigation. Okay, here, during the day, what they do is that there is sun which it reaches its highest point. The local noon, sailors measure its angles. They measure the angle from the altitude, which give them, there is north here. We can see that this map is divided into two. There is the North Pole here, and then there is the South Pole, and then here is the equator. So we have just discussed about the history of navigation, how they use star, suns. So next we are going to talk about the tools, which tools is helping them to navigate. So first in our discussion, we are going to talk about cross star. Here we can see someone holding the cross staff to demonstrate angle measurement. So this cross staff, it helps the sailors to measure star angles. If they dare to stay at the sun or to contrast modern GNSS receivers. So here, what they do is that they close one of their eyes to help them measure the star angles. This is the cross staff. So next is the back staff. So let's talk about the back staff here. So imagine you are staring directly at the sun. Day after day, many navigators went blind because I could remember in one movie that is a very famous movie that they have navigators, sailors that only have one eyes because of how they stay at the sun. So next in the tool, we have the Chinese compass in the Han Dynasty around 206 BC to 220 AD in China. This is the invention of China, which helps in navigation. So next here is a magnetic stone, is another tool also for navigation. And then here we have another navigation tool as well. The backup is called the backup. So next we have the gyro compass. So the gyro compass, we have a Dutch inventor called Marinus Gerardus van der Bos, created the first gyro compass. It's a non-magnetic navigation tool using fast spinning disks and earth rotation to find true north. So the advantage of this gyro compass, it works perfectly at the magnetic poles where traditional compass fails, or it's unaffected by any metal interference or shifts. It provides true geographic north. So now we are progressing. From the compass, we have the gyro compass, and then it became a critical for naval navigation and later aircraft. So in today's gyro compass guide, it guides massive cargo ships, nuclear submarines, and satellite systems. So here is another navigation tool. The key features of this navigation tool, it's a magnetic tool that relies on the Earth's natural magnetism. Its needle always points towards magnetic north, always towards the magnetic north, and its simple, durable design requiring no power. Its historical significance, it's enabling us to save ocean navigation when combined with charts. It has revolutionized the global exploration and trade routes, and it remains a critical backup in modern navigation. as well. So next in line is the modern magnetic compass. Here is a picture of a modern magnetic compass. So next, in the most popular navigation tools, we have the quadrant, we have the astrolabe, and then we have the sextant. So here, the quadrant is used to measure star, sun, the altitude, aligning with horizon. Its impact is that it enables early Mediterranean sailors to estimate latitude. But is limited to fair weather and daytime use. Next, we have the astrolabe. The astrolabe, its sophisticated brass calculator with the star maps, solved multiple astronomical problems. Advancement could determine the local time, prayer time, celestial positions. And then next we have the sextant. Sextants went from back to 1731. It's an idea of John Hadley. He used to measure accuracy of almost 0.1 degrees, and it could be used in rough seas. Next is the challenges of navigation. As we can see, so in the tools, we have a lot of tools, from the compass, gyro compass, the magnetic earth, and then next, we are going to see the challenges. Why are they coming up with a lot of innovation, a lot of ideas for just one thing, just to navigate from point A to point B? So navigation was a big problem. It was a big problem for centuries. Sailors faced navigational crises, crossing oceans without knowing their exact positions. They used the sextants, as we mentioned earlier. They used the magnetic compass, and there is a depth reckoning which estimate east-west positioning using speed. Direction, time. So the catch here is that even 95% accuracy meant 175-mile error. Now we are talking about centimeter level errors. Back then, even 95% accuracy was what? Was 175 miles of error. So here it's the problem. How do we determine the longitude? How do we determine the longitude? On October 22nd in 1707, a fleet led by Admiral Sir Cloudesley, he came up with date reckoning error of over 2,000 sailors drowned, all because they couldn't determine their east-west position at the sea. They all drowned. The disaster forced England to act. Queen Anne, back then, she offered £20,000, that is 4.7 million of today, to anyone who could solve the longitude within 1 degree, that is 30 miles at the equator. For the latitude, they use the sextant, direction, they use compass, speed, they use long line. So every 4 seconds of clock error meant 1 mile of longitude miscalculation of sea. So here is the rotation in 1 degree on equator, 60 miles is equals to 1 minute. So as we mentioned, navigation was still a big problem. There was a big price for it. So who got the prize? John Harrison. Yeah, you guessed it right. John Harrison. John Harrison won the prize for it. It took him decades to come up with the idea, to come up with the innovation. So John Harrison is a self-taught Yorkshire clockmaker. He's named, the best of his time. He claimed the ultimate prize. So he came up with the marine chronometer, a clock so precise that it could keep time within 8 seconds during a transatlantic voyage. Here is the picture of John Harrison's and the clock he came up with. So here is, we see navigation by watch. Okay, so if you guys are still using an analog clock, so the step for you to know the true north in your clock is to first set up your watch to 24-hour time. Let's say now we have, it's 4:20 p.m. to 4:20 p.m. Yeah, then you divide it by 2, which is 8:10 a.m. Then the next step, you let the hour of the hand point to the sun. Then from there, that's the point of the north. So in the southern hemisphere, but that is not the same, it's not the same issue. When you use this method, it does not work for the southern hemisphere. For the southern hemisphere, you now change it down to the mirror. 12 will point to the south. Next in line, we are going to talk about pre-GNSS electronic error. So under the pre-GNSS electronic error, we have inertial navigation systems and we have radio navigation system. So step 1 here, we are initialization. There is initialization for the inertial navigation system, which gets position velocity from GPS or manual input. And then step 2, early acceleration and rotation. And then step 3, it's operate completely self-contained. Error grows from 1 nautical mile per hour without GPS correction. So in the early navigation, that is era before the GNSS birth, we have the inertial navigation, radio navigation, and many more. So we are focusing on 2. Next, we are going to talk about radio navigation systems. So here, radio navigation system, it creates an invisible global guidance, networking-based station like BOR, NDB. These are the systems, are the backbones of GNSS. Next, we are going to talk about the LORAN-C. So the LORAN-C was a globally deployed low frequency. It's a globally deployed low frequency system that provides precise positioning and timing using 100 kilohertz ground wave transmissions. And it's used to measure the difference of signal received from at least 3 synchronized terrestrial stations. Users could determine their location within 100 to 500 meter accuracy. This hyperbolic navigation system operational from 1957 until its US shutdown in 2010. That is the LORAN-C. Here the LORAN-C, we can see it provides almost 0.2 nautical mile, that is 460 meters absolute accuracy. So that is to say that in GNSS time, 24,000 kilometers of satellite give 24,000 kilometers of satellite gives 3 meter accuracy anywhere. This shift from ground waves to safe waves revolutionized navigation economics. This is the map showing the LORAN-C, the coverage of LORAN-C. Its key regions include the North Atlantic, the North Pacific, the Mediterranean, Asia, which includes China, India, with limited deployment. Next, we are going to talk about GNSS. GNSS is a satellite-based navigation system that provides global positioning, navigation, timing. Is a services that transmits radio signals. So we have talked about the radio navigation systems. So it signals radio signals from orbiting satellites to receivers on Earth. So the simple definition of GNSS is it is a technology that helps our devices, like our phones, our autonomous cars, to find our position. Where are we? To find the speed in our cars and to know our time. These are the key GNSS advantage. It has a global coverage. It is all weather. That means it is unaffected under rain, fogs, storms. It has a real-time positioning. So real-time positioning means up to 50 times per second. That is, versus minute is equal to, compared to the traditional distance, it is much, much better. It's in real time. It has high accuracy. So the standard GPS has accuracy of 3 to 5 meters. Now you can see how we came from the ancient navigation to GNSS. We made mention that the best of the ancient navigation was 175 meter error within 95% accuracy. Now we are talking about 3 to 5 meters in GPS, and it could be enhanced with RTK, precise point positioning. And next, here we mention PVTA. So it stands for positioning, velocity, timing, and altitude, which are the key to navigation. So next, we are going to talk about the birth and development of GNSS. We just had a brief discussion of what GNSS is, what it does. We just mentioned that GNSS is a technology that helps our devices to find our location, to know our speed and time. So now we are going to talk about the birth of it. So under the outline, we are going to talk about the history of satellite navigation. Since global navigation satellite systems, the key of GNSS is satellite navigation. Next, we are going to talk about the history of GPS. So the name is being interchanged. Most of the time, you may be familiar with GPS. So we are going to talk about its history, how it started, and then the overview of GNSS in general. This is the first artificial satellite. So guys, you know, the moon is a natural satellite. So we have an artificial satellite. So the artificial satellite on October 1957, USSR, now Russia, launched Sputnik 1, the world's first artificial satellite. This 58 centimeter polished metal sphere with 4 radio antennas marked the birth of space age and secretly satellite navigation. So next, after Sputnik was launched, it inspired the US scientists led by John Hopkins students. So when Dr. William Gu and George Weifenbach at the John Hopkins made up a discovery by analyzing the Doppler shift in the Sputnik radio signals, they could calculate the precise orbit using only ground-based receivers. So what the idea they came up with is to say, okay, what if we can track a satellite from Earth? They had an idea to say, okay, if we can track a satellite from Earth, so why won't we revise the same method? Then to revise, to say, okay, let's track the Earth from the satellite. That was their idea, and it was a brilliant idea. So next, we are going to talk about the US Navy Polaris submarine fleet, which came with the idea of transit. Transit was the right flyer of satellite navigation, but it was revolutionary. It has a constellation of 2 types, the spacecraft designated at Oscar, pictured left here, and Nova, the right. Other names is Doppler Navigation Satellite System, and is also named NNSS, that is the Navy Navigation Satellite System. Hello? It's like my network went off. Hello.
Yeah.
Can you hear me still?
Yes, we can hear you.
Okay. Sorry for that. So next we are going to talk about the history of GPS. So the history of GPS started with NAVSEC, which manages the concepts that debates between the various satellite navigation groups. In 1973, the Pentagon came up with a meeting to show the merge between the Navy and the Air Force into one systems. They had meeting after meeting. They call it the 621B program, which birthed the GPS idea. So here are some historical concept of the GPS key events. In 1973, the Pentagon merged competing Navy, as we mentioned earlier, and the Air Force to come up with a satellite program to form the GPS Joint Program Office. They came up with office first in first, and then they blasted into orbit in 1978. Gradually, they blasted into orbit in 1978, which is a primitive prototype with just 3-year lifespan. But it proved its core idea. Satellites could guide us anywhere on Earth. Next, after 15 years, from 1978 to 1993, the military started testing the Standard Positioning Services, the SPS, which is open to civilians in 1993, thanks to President Reagan of the US. And then next in 1994, the FAA approved the GPS for aircraft navigation. So the FAA is an organization for aerospace. So it changed the idea for pilot flying in fog and over the ocean. Now the pilot could fly in the ocean or in a bad condition in the sky. So in July 1995, the US announced GPS had reached its full operational capability with almost 24 satellites. Next, in between 2000 to 2007, that is the modernization era, which has a frequency of L2 and L5 for civil signals. It announced a better accuracy, anti-jamming, cannot jam the network, and it has permanently removed GPS 3 satellites in 2007. And then in 2010, GPS as national infrastructure. By 2010, it was a national infrastructure. President Obama announces it as a policy. They came up with a policy which includes GPS. So here we are going to talk about the overview of GNSS. Global Navigation Satellite Systems. So examples of the GNSS has the US popular name as GPS, the Russian Globanaya Navigationaya Sputnikvokaya Sistema of Russia, GLONASS, and Chinese Beidou, and European Galileo. These are global coverage GNSS. And then we have some regional GNSS of Japan and India. So next, here in the US GPS, we have 31 MEO satellites, 6 planes, 55 inclination, 55 to 56 inclination. It has an accuracy of 3 to 5 meters. It's using SPS, and its key features include dual frequencies, dual frequency L1 and L2 since 2005. and then its service started in 1993. Next in line, we have GLONASS of Russia. It has an orbit of 24 MEO satellites, accuracy of almost 5 to 10. So for the US, we set 3 to 5. Then for Russia, we have 5 to 10. And it's superior high latitude coverage. It has a superior high latitude coverage, and it's also operational since 1993. Next, we have China's Beidou, or Chinese Beidou. So the Chinese Beidou has 35 satellites. It has an accuracy of 1 meter within the Asia Pacific and 3 to 5 meters for global coverage. Its unique features include short messages for emergencies. So we had a scenario whereby we tested in our lab. We used the Beidou to send a short message. So here is to say that if there is an urgency or emergency, you can send a message and you can receive a short message, which is the unique key feature of the Chinese satellite, the constellation. Next, we have European Galileo. For European Galileo, it has 26 plus to 30 MEO satellites. It has an accuracy of 20 centimeters. It's an open service for now. And next, we have the regional systems of Japan and India. For Japan, it is focused in the East Asia. And then for India, it has around 7 satellites, which focus on South Asia. And then it has an accuracy of around 10 meters. Here next, we talk about SBS. So what does SBS means? Satellite-based augmentation systems are some heroes of precision navigation. They correct GNSS in real time. So if the GNSS has an error, they correct it. They boost accuracy as well from meters to centimeter levels, which is critical for aviation and autonomous vehicle, self-driving cars. So the major SBS systems and their latest upgrades include the UWSE. It has a key feature of supporting the aviation with Cat 1, and we have European IGNOS, which is integrated with GPS with the European constellation Galileo. It has a frequency of L1/E1 plus L5 and E5. So if the Galileo and GPS combine, it gives 1 meter accuracy. And then next, SDCM of Russia, it is an expansion. It's an expansion in 2020, which added L1, L3, and L5C signals. It has a specialty of optimized correction. And then next, we have BDS SBS of China. It is launched 4 geosatellites. So it's a global augmentation system. Next, we have the Japan here, and then Australia here, which has tested for multiple sectors, including agriculture, mining, aviation. And then in the future, they have a plan of drone navigation. So is what we talk about, the satellite-based augmentation system for correction of GNSS. Next, we are going to talk about the launches of GNSS satellites. So for the past 4 decades, we have seen an explosive growth from 1978 to 2020. We have seen an explosive growth. First, it was launched, and then gradually it kept on launching, and it grows on. So today, your phone unlocks 2 to 3 times more satellites than in 2010. Next, we have the GNSS applications. Under the GNSS application, we are going to talk about how GNSS reshape modern science, military navigation, time, mapping, personal navigation, precision agriculture, and traffic control. So, application in science. Under application in science, here we have a sketch of a snapshot of a cliff in Zone 4 in Japan. So here we are about to witness a picture. Here it was a picture of an it's a picture of an earthquake. So they were able to snap some pictures of the ground movement in real time, which helps the earthquake and study fault lines. Next, we have a melting ice, where it's another scenario for GNSS. A melting ice sheets in the Greenland and Antarctica, here in Greenland and Antarctica. So if Greenland melts, e.g. if Greenland melts, sea level might actually fall due to what? Due to loss of gravitational pull. So next time you hear there is 7 meter of sea level rise, remember it's not just about water. It's not just about water, but Earth's entire dance of ice, rock, and gravity. Entire rock, ice, and gravity. Next, we have its application in transportation. So, application in transportation, we have UAV rail. Here you can see a picture in our lab. I'm holding a drone. So have you guys ever wondered what a train app looks like exactly? So, or how does it work? So there is an onboard GNSS plus a ballistic tag. It combines GPS, Galileo, all the constellation, and it transponds to almost 10 meters of accuracy. It gives data in real time. That's how the rail works, the application, if you ever wondered how it works. Next, we have application in agriculture. So the application of GNSS in agriculture, it helps in precision soil sampling, accurate field navigation, crop spraying, tractor guidance. So for precision soil sampling, we could collect data, analyze and localize variations of chemical application. For spraying of crop, we can use spray fertilizers. So there was a scenario where I had a discussion with my supervisor some days ago. He came up with an idea to say, okay, what if we are using a drone here as seen in this picture to spray a pesticide for a large farm instead of using a manual or human labor. So you can see how GNSS could help in precision agriculture. It came a long way. Next, we have another application. This application deals with the market share and then global development. We are going to talk about the economy. Here, the modern receivers now tap into multiple satellites. The GPS has almost GPS plus BDS plus Galileo receivers are capable and available now from numerous receiver manufacturers, especially for production of equipment and mobile devices. Next, we are going to talk about the market share of GNSS. It has an estimated annual growth of 8% from 2013 to 2023, according to the European GNSS agency. So the market is growing huge, 8%. And then from 2021 to 2031, is expected to grow at a CAGR of 9.2, which is equivalent to almost 500 billion pounds. Still according to the European Union for Space Program Agency. Here is the regional market distribution. So you can see here in Africa, the market distribution is 0.2. So if we remember, you said our reference station is just 3%. So if we have our own constellation, it could be better. If we have more reference station, it could be better. And it will go a long way. So in our today's reference, we have used some textbook and then a publication of our topic, which is available on Springer, the evolution of GNSS. And then we look at some of the old textbooks from 2005 to 2010 and some modern ones between 2020 and research papers in 2025. Thank you very much for listening to this presentation. And I will be expecting your questions and comments. Thank you very much.